Hi everyone, so we've made a start on alcohols, which will feel quite similar to the alkenes topic, and there's actually quite a lot of overlap between the two. However, doing this topic is going to require us to remember our intermolecular forces. So I thought I'd put this quick video together just to remind you a bit about this. If you found the bonding topic hard, you might want to look back in your bonding booklet at the 3 intermolecular forces. And the chances are you did find it hard because it is quite tricky and we are going to need to be confident on it. Let's just quickly recap by comparing these 3 molecules I've got here. So I've got an alkane, a haloalkane, and an alcohol. So of course the alcohols are what we're going to be talking about mostly in this topic. So of the 3 intermolecular forces, which ones are present? And most importantly, which one's the strongest in that molecule? So the weakest type of intermolecular force is the van der Waals forces. For that, we need a big fuzzy cloud of electrons floating around the molecule so that the molecule can talk to another molecule, say over here, and talk to its fuzzy cloud of electrons. Well, do all these things have electrons? Yes. So they all have van der Waals forces that can act between the molecules. The next one to look for, do they have dipole-dipole forces that can act between the molecules? Well, for that, we would require 2 atoms bonded together that have a very big difference in electronegativity. So fluorine, as you should know, is the most electronegative element, and that has a higher electronegativity than carbon. So in this molecule, we are going to have a dipole forming. The dipole can act a bit like a little bar magnet in this molecule to interact with another molecule. In this one, the alkane, there's no 2 elements with a big difference in electronegativity, so we're not going to get any dipole-dipole forces. And this one over here, well, we've got oxygen. Oxygen is the second most electronegative element. So yes, we are. Dipole-dipole forces present. Dipole-dipole forces present. The last one is the hydrogen bonding. Careful, it's a bit of a phony word. That is not a type of bond, it's an intermolecular force, like these other 2 we've looked at. We need to have a hydrogen atom bonded to oxygen or fluorine or nitrogen. Well, we've got fluorine here, we've got hydrogens, but they're not bonded together. So no hydrogen bonding for that one, but we are going to get hydrogen bonding here. And so, as we decided, the thing we're after is the strongest intermolecular force present. That's the thing that's going to determine the properties. The strongest force present here is the van der Waals forces. Strongest there is the dipoles. Strongest there is the hydrogen bonding. So that's just some recap. Right, next thing. Of these 2, we're not going to worry about the haloalkane. Are they soluble in water? For this, I'm actually going to come out of the presentation. So what I have here is my my 2 molecules, and let's see if I can dissolve them in water. Here's my water molecules, and they're happily hydrogen bonding to each other. You can see I've drawn them in this way so the hydrogen bonding is easy to follow, and you are going to be able to complete diagrams like this. So for example, in Key Assessment 4, question 7, you were asked to look at the hydrogen bonding in something similar to this, an alcohol actually. And everyone should have got full marks on that. So again, have a look at Key Assessment 4, question 7 to help you understand what's going on here. Basically, I've got a great big vat of water and all the molecules are happily hydrogen bonding to each other. They're not going to want to stop doing that. They like it. They like these hydrogen bonds forming. It makes them happy, if you like. So if we were to try and mix something else in them, that's what the soluble bit means. It means if I try and mix them, are they going to mix up and dissolve? Or are they going to separate and form 2 different layers? If they were going to mix, these happy hydrogen bonded water molecules would want to be able to form a hydrogen bond to the new thing. So let's say that I try and get this alkane in. I'm going to be getting rid of that water, so I'm losing some nice hydrogen bonds there. I'm dumping this alkane in. am I gaining a hydrogen bond between this hydrogen and this lone pair of electrons? Well, no, I'm not, because we decided this can't do hydrogen bonding. Its strongest intermolecular force is the van der Waals force. So that one's not going to want to dissolve. But you can probably see where this is going. Over here, I've got an alcohol. We decided that can do hydrogen bonding. There's that hydrogen there. So if I try and mix that up with my waters instead, we are going to continue to have that nice hydrogen bonding interaction. So you could think of it as these water molecules are happy to welcome ethanol into their sort of party where they're all doing hydrogen bonds, but they would not be happy to welcome ethane because it can't join in with the hydrogen bonding. We don't want that. That is what leads to this slightly complicated looking diagram here, which you've got, which just shows two molecules of ethanol in amongst those three water molecules and some green dots are the hydrogen bonds. So that's just showing the 3D structure of the molecules there. Okay, and that's the gist of what I want you to take away. If we were still in class together, I would probably give you this starter to look at, which looks a bit complicated at the moment. Maybe it's too complicated, maybe I'd change it. But anyway, which is more soluble and why? So this time we're going to compare, instead of comparing ethane to ethanol, we're going to compare a sort of batch of 5 molecules of ethanol and a batch of 2 molecules of pentan-1-ol. Which one of these things, if I were to chuck it into some water, which one would be more likely to dissolve? That would make it more soluble. And the reason I've chosen these two sets is if we look at the carbons and hydrogens, there's the same amount of carbon in these two things, and I haven't actually worked it out, either the same or a similar, very similar quantity of hydrogens in these two things. So you might expect it to be quite similar. But of course, the important thing is how many hydrogen bonds can we form? And so we're going to be having to look at how many oxygens there are. If you're mathematically minded, you could think of this as a ratio. What's the ratio of number of oxygen bits that can hydrogen bond to these big carbon hydrogen bits that can't hydrogen bond? Well, if you've got loads and loads of carbony bits that can't hydrogen bond and only a small quantity of oxygeny bits that can hydrogen bond, then the thing's not going to be particularly soluble. So basically we need to look at the molecule and we need to decide, okay, is it like ethanol from the last slide? Or does it have bits like the ethane from the last slide? Does it have big bits of the molecule that don't have any hydrogen bonding on them at all? Well, ethanol, we decided, is quite soluble in water. So this is the answer to the question. Ethanol's more soluble in water. If we try and think of the pentan-1-ol as being soluble in water, we're going to have to look at this long bit. Next, let me get my pen out. We have this long bit of the molecule here. Let's say we take that. It's all just carbons and hydrogens. No polar bonds at all. A bit like the ethane. So that chunk of the molecule doesn't want to dissolve in water. Whereas this chunk here does, but there's only one hydrogen, there's only one oxygeny bit that can do the hydrogen bonding per molecule. Let's be clever and change colour pen. So this bit of the molecule, so I take that chunk, that's a small bit that wants to form hydrogen, that can form hydrogen bonds, and I can only circle those two. Okay, so I've got a big bit of red there, which isn't going to want to form hydrogen bonds. Whereas I could put loads and loads of these blue circles over here, lots of hydrogen bonding possibilities over here. Okay, thanks for watching.